Hello everyone. So today I'm gonna continue discussing the last part of the stability for variable weighting method. So we talked about backward Euler, forward Euler, and finally I wanna show the stability criteria for variable weighting. And after that we are gonna move forward with the time marching methods. I'm gonna introduce predicted corrected Euler method or corrected Euler method, then Rangakuta methods, and then in the next lectures probably we'll start looking at one stage much step methods such as Adams-Bashforth. Okay. So before getting started, I just wanted to make a note that these methods, these stability criteria that we are investigating is only for initial value problems, and we will have a more in-depth stability analysis after we talk about spatial discretization as well. So we are going to combine these temporal or time discretization with spatial discretization that we learned before, and then we will come up with a more general stability analysis, which is kind of also sometimes called von Neumann stability analysis. Okay, so this is just the preliminary step toward that. So I want to get started with the last method, which is variable weighting. Right, we talked about backward Euler, forward Euler, and this is variable weighting. So let's see how it is, how it looks like. So if this is time, so this is time. So this is Tn, say this is T at step n. And then here, say we are at Tn plus 1. Okay. So if we use the information at Tn, right, if we use the information on f, if we evaluate f, which is the right hand side of our equation, if you see it here, let me see if I can bring it here, right? If you evaluate f at n or t0 here, it's called forward Euler. If you evaluate it at t1, if you evaluate f at t1, it is called backward Euler, right? So here we have the same phenomena. If we evaluate it at tn, it is forward Euler. If we evaluate it at tn plus 1, it is backward Euler. And if we evaluate it in the middle, somewhere like here, say, it is variable weighted Euler. Okay. And this length is theta delta t. Okay, so this is the length for this variable weighted Euler method. Okay, so let's see what it was. First, look at the method for this kappa u. Say, for example, for this kappa u, we are gonna evaluate it at tn plus theta, which is going to be un plus 1 minus un over delta t plus kappa theta times u n plus 1 minus theta un. So if theta is 0, it is gonna be backward Euler, forward Euler. If theta is 1, it is gonna be forward Euler. Okay, so this is the approximation we have, and it is order 1 minus 2 theta delta t and delta t square, right? So if theta is 1/2, it's going to be delta t square, order delta t square, otherwise it's going to be order delta t. So let's rearrange these terms. So I'm going to rearrange them. It's going to give me 1 plus kappa theta delta t un plus 1 equals to 1 minus kappa 1 minus theta delta t times un. Okay, I just rearranged the terms here. And got this equation, and now I want to write un plus 1 equals to 1 minus kappa 1 minus theta delta t over 1 plus kappa theta delta t times un. Okay, and this is, we can just write it as lambda times un. Okay, so the condition for stability that we had was lambda should be smaller or equal to 1. So let's see what does that imply. So 1 minus kappa 1 minus theta delta t over 1 plus kappa theta delta t should be smaller or less than 1 or greater or equal to minus 1. So the left one is going to give me minus 1 minus kappa theta delta t. The left condition is going to be, should be smaller or equal to 1 minus kappa delta t plus kappa theta delta t. Okay, so this means that I'm gonna have, just by rearrangement, kappa, if I factor kappa delta t, I'm gonna have yes, the first one is gonna be 1, and then I'm gonna have minus 2 for these two ones, 2 theta. This should be smaller or equal to, and then I take 1 to the other side, 2, right? So this is the first condition for stability that I obtain, and the second one is for this condition. Let's see what does that imply. So that implies 1 minus kappa 1, let's say minus kappa, then I have, minus kappa delta t. So minus kappa delta t plus kappa theta delta t should be smaller or equal to 1 plus kappa theta delta t. So these two are going to cancel out, and these two ones are going to also cancel out. So this means that delta t should be greater than 0, which it already is, so it's a trivial condition which we don't care. So it's always okay. So only we have this condition for stability here. Okay, so let's see what does that mean. So here you can see something. You can see that if theta is greater, or equal to 1/2, this is gonna be, so let me put it this way. If theta is greater or equal to 1/2, this is gonna be smaller or equal to 0, right? So this is gonna always hold. This is gonna always hold if theta is greater or equal to 1/2. How about if theta is smaller than 1/2? If theta is smaller than 1/2, then kappa delta t should be smaller or equal to 2/1 minus 2 theta, right? Because this is going to be a positive number now. So we will have this condition. So it is kind of conditionally stable here. Let's look at it more carefully. So I'm going to write it down here. So if theta is smaller than 1/2, meaning that this is going to be positive number, then kappa delta t should be smaller or equal to 2/1 minus 2 theta. On the other hand, if theta is greater or equal to 1/2, then it's going to be always stable, as we know that, because this is going to be a negative number, and so it's always going to be smaller than 2. It's going to be a negative number on the left hand side. Okay, so this is a conditional stability here. We have a conditional stability here. Conditional This is conditional stability. And if it is greater than 1/2 theta, then we will have an unconditionally stable. So here, actually, the best value we can take for theta for this problem is theta equals to 1/2. And the reason is because of two things. It is both stable and second accurate. So second order accuracy plus unconditionally stable. So this 1/2, as we noted, it's gonna be a Crank-Nicolson method. So you can have, if you put it just right here in the middle, then this is gonna be second order accurate, and your problem is gonna be unconditionally stable. So you will not face any stability issues. Okay. So this was the stability of Euler methods that we investigated. Kind of want to wrap up. As you see, for explicit Euler method or forward Euler, we had a conditional stability. that we noted here. For backward Euler, it's going to be always, or implicit Euler, it's going to be always unconditionally stable. So your solutions are not going to blow out in time. And for variable weighting, we also have, depending on theta, we can have conditionally stable or unconditionally stable method. So this is very important, especially when you discretize your solution and you want to solve it numerically with any code, like any programming language. This is very important phenomena to note, that sometimes you will see that your solutions are blowout and you get like inf or nan in those codes. And the reason for that is, one of the reasons could be because of this stability criteria that was not set properly. So you need to set your delta t's properly based on these conditions that, for example, are shown here, okay? Depending on the method that you are using, and we are going to go more into this, delve into this problem, stability, when we talk about also add the spatial discretization on top of this temporal discretization, and when we talk about von Neumann stability criteria, which is a general method and approach for finding the stability of these numerical schemes. Okay. So now I want to start the second topic, the next topic, which I'm going to go through the numerical methods, some famous or some well-known time-stepping methods and time-marching methods. So you have some options when you want to discretize your PDE in time. Okay, so the first one I want to start with is Euler method and corrected Euler method, to be more precise. So these are the simplest actually kind of methods that for time marching that are very intuitive. So it involves, and we talked about two of them, Tn to Tn plus 1. So you are only having one step, right? You're one step in time. So these are also, that is why we call these methods as one step method. You go from Tn to Tn plus 1. But to get higher order approximation, we use greater than one step. So we use more steps in time, like rather than Tn, we can go to Tn minus 1, Tn minus 2, and other steps, and or greater than one stage. So instead of just this stage, we can have multiple stages. So for example, for one step that we have from Tn to Tn plus 1, for example, like variable Euler method, variable weighted, we can, or Crank-Nicolson method, so we can have some stages in between these two, okay? So an example, let me just show this example. This is corrected Euler method. So corrected is a two-stage and one-step method. So in general, Euler methods are one-step methods, so we can just increase the stages to be able to increase the accuracy. And for multi-steps methods are the next topics we will talk about them, like Adams method. Those are the other type of methods, okay? But Euler methods are typically one-step method, and we can have one stage, two stage, or higher ones, okay? So let's see how it is. So the way we are going to define it is U star is a kind of a middle stage. Solution is UN, or the just what we call as forward Euler predictor step. So it's just a simple Euler method, forward Euler. We just use a simple forward Euler method, where du over df is du over dt. Du over dt is equals to the f, which is f can be any function, and so you evaluate the function at step n, and this is a forward Euler. And then in the correction step, what we do is, so the first one is called prediction step, and the second one is correction step, where we take that un again and then add delta t 1/2 of step of n plus 1/2 of u star and what? So we take u star now and tn plus 1. Sorry about that. So as you see here, so we now have this 1/2 of fn, and then we add that with this fu star from here. Right? So we use u star here. So the first equation, so this is the corrected Euler. First equation predicts un plus 1 using forward Euler. Right? So this is the first equation. And then the second equation. So let's see what is that. So second equation corrects the prediction. Okay. So the first step is a predictor, and second step is corrector. We correct that prediction that we made before. So this is called, based on this, predicted corrected method. Okay. So this is the first step, first method, and then the next method that we are going to talk about is multi-stage one-step method, which is a more general of that. So this corrected Euler is going to be also a subset of that, which is called Runge-Kutta. I think most of you probably have heard it before, but we are going to talk about Runge-Kutta. Rangakuta methods, and we are going to show different ones like two-stage and the most popular one which you have probably heard, which is four-stage Rangakuta method.